So we are starting now.
Okay.
Today it's going to be John Murray speaking about the Firmware stack management with OpenBMC. So we just wanna we were talking about this, like how many people know OpenBMC or like what that is, or you need some intro.
I don't know anything about it.
Okay. Okay.
Did you leave that server on the free hardware table at
Yeah.
OSFC?
Yeah,
Yeah.
that's okay. Nobody took it. That's amazing.
No, people. No, some people were considering it.
I was okay with it, so in some way. I don't care.
Yeah. So I'll hand it over to you and I'll
Okay.
let you give the
Thank you.
intro.
Okay, so my name is Jean-Marie Verdun. That's French. It's not easy to pronounce, but that's okay. So you can make mistakes with that. So I work for HPE. I used to work for Digital Compact and HP back in the 90s. And I created my own company in 2006 that I sold in 2018. So I've been working for a huge company. I had my own startups, successful exits, and came back to HPE. I was based in France during my Digital Compact, HP, and my company. And we moved in the US when the company got acquired in 2018. My company used to work on designing hardware in France and Europe. We mainly had customers which were focused on defense. And then we started to work with some hyperscaler in the Bay. We were having a very weird approach when we designed hardware. So we were focused on energy efficiency and sharing our knowledge. So roughly we are doing open hardware stuff. So we got I think we were the first OCP member in Europe in some way. So we started to work with the OCP Foundation back in 2012. So and the foundation has been created in 2010 or 2011, I don't remember exactly. And I started to work on Linux boot with Ron Minnick. Ron cannot be there today, but we know each other for a couple of years. And I used to work on OpenBMC for about a couple of years too. So, and today is about OpenBMC, what we do at HPE regarding OpenBMC, and where we are focusing our effort with our, I would say, customers, partners, or anybody who is willing to work on OpenBMC. So just to give you a rough intro on, of OpenBMC, so you probably know what a server is. You have to answer yes or no.
Motherboard, server,
Yeah.
A server,
data center.
a
server.
data center server.
Okay.
Okay. So within each servers there is a remote control features, which gives you access to the machines to power it up, to power it down, monitor the status and the health of the servers.
Okay.
If there is any failures inside the machine. So there is roughly like a black box into the server, which is giving you full control, full remote control of the machine. So you don't need to go to the data center. You can access to the video, you can access to the local storage health, and you can control the fan speed and everything through that device. That's called a BMC, Baseboard Management Controller. And
What management?
Baseboard.
baseboard,
Baseball.
baseboard management
It's
controller.
basically management or control plane, you can say, for the data center server hardwares.
So it was very basic at the beginning. So it has been created by Compaq, who is now HPE. And the initial features was just, I want to turn on and off the machine remotely. And then I want to get access to the display just to install Windows, because back in the 20s, the Windows servers market share was pretty huge. And it was needing a video card just to be configured, so you couldn't connect remotely through a serial console or SSH. That didn't exist. So Compaq has created a lot of innovation around this. Everything was designed through proprietary solutions. It was based on very basic ARM CPUs without MMU most of the time. So no virtual memory and very small memory footprint. So the early version of the BMC was using deep embedded operating systems. So it couldn't run Linux, it couldn't run advanced operating systems. But with time going on, the performances of the BMC ASICs have improved. So two reasons for that, standardization and cost of manufacturing. So it's pretty easy just to put a decent ARM chip, even a 64 bits one, into a $5 parts right now. And that's roughly the amount of money you want to put into a BMC. You don't want to put more than $5 into your BMC parts. And back in the 20s with $5 you get nothing, or roughly very basic hardware. So in 2024 you get something which can boot Linux. So that's the beauty of the manufacturing process advance. So we are now able to boot Linux on the BMC, and Compaq has kept, and HPE has kept strong legacy with the BMC side. So we developed the ILO stack by using an operating system from Green Hills. You are probably not familiar with that company.
No, I am.
Okay, that's a company which is designing embedded operating systems for real-time applications. And that's the OS we were using just to develop the ILO stack. The ILO stack is the name of the proprietary firmware which run on any HPE BMC systems right now on the ProLiant family.
Is Green Hill that's in Santa Barbara?
I don't know where they are headquartered, but
I'm pretty sure I've seen them in.
It might be there. Yeah.
Yeah.
I'm not sure, but it might be there.
No, because I went to college there, and I'm pretty sure they were at our career fair.
Yeah, it could be the case. Yeah, it could be the case. And we kept Green Hills forever, but with the expansion of Linux, so we believe that might be a good opportunity to give more diversity to our customers, and we offer that capability on the ProLiant family now. So they can select between the proprietary open source, the proprietary firmware from HPE, which is ILO, or OpenBMC. So just some past about OpenBMC. So OpenBMC has been created about, I would say, 6 to 8 years ago. It was the outcome of an hackathon organized during an OCP summit on Facebook campus. And it was targeting first the BMC, which was embedded into a top-of-rack switch called the Wedge 100, which was the, I think it was a 48 port or 32 ports, 100 gig Facebook data center switch. And Facebook wanted to create some more innovation within the control plane of their networking stacks. And they were upset about the proprietary solution that the vendors offered them, and they took the decision just to create something which was more open. And during that hackathon, they ended up creating the first version of OpenBMC in some way, which was very basic by that time. In parallel, Google had a project with IBM just to launch an open power server. I don't remember the code name of that machines, but with Rackspace. And they also needed an open source BMC software stack for that machines, which has been contributed back to the OCP Foundation. And they started another OpenBMC project. So in some way, during the first few years of the open source BMC stack, there has been two projects in parallel. The one from Facebook and the one from IBM, Google, and Rackspace. And a couple of years ago, they took the decision just to merge both of them and call it OpenBMC. They brought the source code to the Linux Foundation, and it's right now driven by Patrick Williams, who is working at Meta. So he's based in Austin, Texas. And if you go to Google, that's a lady who is handling the OpenBMC strategy. I never remember her name, so I should know her.
I met her. I also don't remember the name.
She's not contributing code, so that's why I forgot. I always forgot her names. She's more managing the strategy at Google than being a contributor. But Sai, who was working at Meta, is working now at Google and is taking care about OpenBMC. So OpenBMC is roughly an open source implementation of the software stack which runs on the BMC. And that part is pretty critical nowadays because this is the control plane of the data centers, as Binal said. And it's pretty important to have something which is highly secure and can properly monitor the behavior of the systems within the data centers. It goes from the cooling to the power management, so how much power does each server consumes, and how can you balance the workload inside the data centers. So everything goes through the BMC for the control plane, and even reporting the hardware error from the servers. So if you get a failing drives, so this is the BMC with inform first or failing DIMMs, and it is going to be recorded into the BMC event logs, and the data center technicians are going to use the BMC event log just to fix these issues. So up to now, OpenBMC was just trying to be a replacement of the proprietary BMC stack. So there is ILO on HP machines, there is IDRAC on Dell systems, and there is also other BMC proprietary BMC stacks which are available from AMI. It's called Mega Rack, if I remember properly, which are available on many ODM systems. So it could be Supermicro or other vendors. So OpenBMC was just a direct replacement. But what we think at HPE is that OpenBMC can be more than a direct replacement than the BMC. If we think that the BMC is running a real operating system instead of running a firmware. So we are roughly exploring, and my role is to explore that shift into the industry. So instead of considering the BMC as being a machine which is running a static image, so when you build a firmware, so roughly you get a build environment, and the outcome is a binary which is feeding into a SPI node. And usually when you want to update everything, you have to wipe out the whole SPI node, and you are stuck with the size of the storage of the SPI node, which is pretty small right now. It's about 16 to 32 meg. So the best case scenario would be 64 meg. But you cannot do that much with 64 meg of storage in 2024. Some people will consider this is huge. Some people will consider this is pretty small. But we are dealing with systems which cost thousands of dollars, or I wouldn't say hundreds of thousands, but tens of thousands of dollars. And just being stuck because you get that specific component which is limited to 32 meg is a little bit upsetting when you think about it. And when you think about the fact that you might be moving away from a firmware approach to an operating system approach when dealing with firmware, you can introduce new concept, and that's the main purpose of that talk today. So if you have any questions, feel free to ask me. If you do not understand some concept, just stop me. We are just 5 people, so that's super easy for me to answer your questions. So the main reason why we explore new things with OpenBMC is also because we get some end users which are requesting us just to explore these things. So the initial feedback that we get from them is they don't want to be locked with their suppliers anymore. So they want to be independent from the suppliers with the firmware, like they are with the operating systems on the server side. So when you purchase an HP machine or Dell systems, you can put Red Hat, you can put SUSE, you can put whatever you want, and you can even build your own Linux. And many of our customers are telling us we want to do that for everything inside the machine. So we want to have the full control of the software stack. The main reason behind it is they want to be able to fix bugs, and they want to be liable for the security of the platforms. And in many cases, our customers are liable for the security of their platform to their customer too. So when you are defense subcontractors, you need to prove that you own the security of the platforms and that this is not one of your suppliers who owns it. So that's the other things. Many of them have different release life cycle too. So we see customers who are telling us, I don't want to update my firmware at all. That's okay. In some cases, it's okay. If the machine is not connected to the internet or not exposed to any threat, you don't need to update. If you know that it works, the recommendation will be do not touch it. If it's delivering the services, so do not touch it. But we also have customers which are telling us, I want to update my firmware every week. So that's the balance that we need to manage. So the other thing is they want to stop the black box approach. I soon spoke about it a little bit. They complain a lot also about the API. So when you handle firmware, you have to discuss and talk with the firmware. So they are all using Redfish or IPMI, but there is compatibility issues between suppliers. So if you are not familiar with Redfish or IPMI, so let's talk about Redfish. IPMI is a slow dying horse currently. The whole industry hopes for its death, but it's not dead yet, but it is coming. So Redfish is a web API just to send command to the servers through, as I say, the web API. So how can I turn on and off the machines? So you just send an API call through a well-known web interfaces. That's published, that's standardized, but the issue is that this has been standardized through DMTF. I love DMTF, but that organization doesn't publish reference code. So they build up API standardization, but it's up to the manufacturer to design the reference code. So, and what happened is that HPE is getting the API, Dell is getting the API, everybody is getting the API, and we are writing code based on our understanding of the API. And if you look at Redfish, just the API documentation is more than 2,000 pages. So, and within these 2,000 pages, you can interpret in very different way the behavior of the API. And this is what is happening. So in some way, some API calls do not behave the same way between Dell, HPE, and other vendors because our engineers didn't understood the same way the documentation. So, and that's the challenge. We try to modify that behavior by telling the DMTF they should be publishing reference code. So when they publish an API, just give us reference code. We can help you to write the reference code. Like that, we can share the reference code between vendors, and that will be fixing that issue. But that doesn't happen. And that is why OpenBMC is adopted at scale currently, because OpenBMC is becoming the de facto reference code in some way, because it can run on any kind of suppliers, HPE, Dell, or other vendors, and that is the exact same things. So this is like when you run Linux, Red Hat on HP machines or Dell systems or Supermicro systems. That's the same Red Hat. So you just learn one time Red Hat, and you can use it on any vendors. So with OpenBMC, that's about the same things. So when you switch from HPE to Dell, that's the same OpenBMC. So if you are using the proprietary stack, you get ILO, you get IDRAC. So ILO is a great tool. I'm not saying it's a bad one. I'm just sharing the feedback from the end users when they have more than one vendor into their data centers. You have a question?
I have just a question. You said Redfish is a internet API, right?
Yes, that's a web API. Yeah.
It's a web API.
Yeah.
So on, I'm not real familiar with some of these architectures. So this BMC, it's a separate processor running to keep the status and be able to control each server.
Yeah.
Now, does it have its own stack that is connecting to the internet?
Yes.
And the network?
Yeah.
No, it doesn't. It's not fed through whatever the main server is.
No.
Okay,
It has a network connectivity, and it's either one dedicated physical port, or in some cases we can use some trick to share the main network interface from the host for the BMC.
Okay, so
it's not recommended to work that way, but that's the two options that you have. Okay. But the BMC is always connected to the network.
So in the box, it looks like its own little computer connected to the Ethernet.
Yes, it's like having a full black box into the servers.
Okay.
And that black box is like a PC. You got a small PC into each servers, which is taking care about the half of the server.
Okay. So then the API is probably some sort of RESTful API.
That's a RESTful API.
With security and stuff.
And with HTTPS, encryption, and all these kind of things.
And like any standard, as you point out.
Yeah.
Yeah. It's hard to write code that actually does exactly the same thing by paper.
Yes, that is the challenge, and that's why people are just complaining about that compatibility issues.
Okay.
And in the end, all of our customers have provisioning codes, which is just checking if this is Dell servers, I'm running that. If this is HP servers, I'm running that. If this is Supermicro servers, I'm running that. And this is super upsetting to them because they need to maintain everything, and that's a big pain. There is also a few other things. The update process of the firmware image, that didn't evolve during the past 20 years. That's always the same process. You get a 64 meg image, you get the new image, and you have to flash it to each servers one by one. There is not that many rollback. So if the flash process is facing an issue, you are losing the server. If you want to roll back because the update is creating more bugs than fixing issues, it's pretty tough just to roll back. So you need to rerun the whole update process. And many people are just complaining that why can't we just update the features where we want to fix the issue? Because when you look at the BMC stack, there is a web server, there is storage controllers, there's drivers, there's many subsystems into a BMC stack. And usually when you face a bug, you just have a bug on one subsystem. And you just want to fix the bug. And you don't want to update the whole image, which contains new features or new stuff, plus your bug fix. So a lot of people are complaining about that. And they just want to have the capability just to fix bugs and not the whole image. And that's not possible today with regular BMC firmware image, even including OpenBMC. So OpenBMC right now, it's really funny because OpenBMC is really a BMC image which is just copying the proprietary world but doing it with open source software. But it's creating static monolithic image. It's pushed to some kind of boundaries which are just a little bit crazy when you think about it. So when you think at HPE, we got probably 12 different servers. And for each servers, when we have to run OpenBMC currently, we have to build a specific OpenBMC image. There's no way for us to have a common OpenBMC image between the whole fleet. So that's because the way the code has been engineered is for the embedded world. So, and for the embedded systems.
Yeah.
So when you think embedded, you try to tweak everything just to save as much space as you can, and you try to build a software which is targeting a very specific hardware configuration. So what we are just trying to do right now with our POC customers and at HPE Engineering is just to break all of that and say, okay, our customers wants to be able just to update one subsystems. How can we do that with OpenBMC? And we have enabled package manager into OpenBMC. And many people whom are working on OpenBMC are just thinking, well, crazy. But we are building OpenBMC image with, RPMs.
Yeah.
So we are just building OpenBMC and we are building RPMs and we are telling our customers, if you want to update just one RPMs, just do it. You can update the RPMs. You don't need to update the whole image. And you can test, and you can remove, and you can roll back. So this is the kind of trick we are working on currently. How can we move from an embedded software stack to I would say, a general purpose operating systems, which is targeting the BMC infrastructure. So, and that's what we are doing right now. The main reason why it didn't exist is the flash memory size. Because each time you want to have something more generic, you need to have more storage space. And I'm going to explain how we broke that issue. So I'm going to share some example, and this is really some real life example that we faced when we started to deploy OpenBMC with end users. And where we are currently standing. So many of our end users are telling us we want zero-touch provisioning. So we spoke about it not last week, but during our previous meetup.
Last meetup, yeah.
Yeah, zero-touch provisioning means HPE send a server into a data center, into a remote place. The customer doesn't have any local technicians. just somebody is racking up the server, but they don't know anything about software or about system configuration. And somebody remotely is able just to provision the machines and trust it. So that is what we call zero-touch provisioning. So I'll be
so it's no on-site
no on-site setup.
It's
Yeah, everything is remote, and I'm trusting the machines. I can run attestations, and I can know what kind of systems just come up into my data center.
Okay.
There is the deployment efficiency. So how fast can I deploy firmware update, and how fast can I deploy new systems? The seamless update process, and some reliable firmware boot. So we got customers which are complaining that in some cases, when they restart the machines too often, the firmware doesn't boot for any reasons. And that's pretty frustrating because they have to send a technician into the data center just to plug back off and on the power.
I did cameras, I just sent it back to us.
So what we faced is the first case scenario was about zero-touch provisioning with OpenBMC, and that's always into the context of OpenBMC. We are delivering a server in Tokyo data centers to a customer, and that customer is based in Paris in France, and they have nobody locally. And they say, I want to be able just to provision OpenBMC on that machines. So, and I don't even know what kind of machine it is. I just know this is an HP machine. I don't know if this is an AMD-based machine, if this is an Intel or ARM-based or whatever. I just know that a new HP machine just is coming up. So the answer that we provided with the customers, because this is OpenBMC, so each time we try to tweak OpenBMC, that's a collaboration between HP engineering and our customer engineering or partner engineering. So we just want to be sure that we are aligned and we are delivering something which is scalable and maintainable. So the decision that we took is we needed to have a common OpenBMC image for all of our servers. So we said we need to be able just to run the same image between Intel, AMD, ARM, or RISC-V or whatever. Because otherwise, it's way too tricky. Because if we, currently with OpenBMC, if you deliver an Intel OpenBMC image which is targeting an Intel servers, that's not going to behave properly with an AMD CPU. And that's not good. Because you still need, the BMC is managing the reliability of the systems, and you need to be sure that it is going to work properly. So we found a way just to build a common image, and that's going to be the next slides, what we have done just to make it work. And that common image is going to boot on any HP machines. So we can do that because the ASICs, the BMC ASIC is designed by HPE, and we know the system's configuration and how we can configure that. There is one trick that we are extensively using. Every HPE motherboard is coming with a system ID, which is non-writable. So that's within an EEPROM, and you cannot change that. And that system ID is unique per server. So we can identify what kind of machines we are going to run on. So, and that's something which is also important to us. Otherwise, we cannot build a common image, because in the end, that common image is going to be very generic at the beginning, and then it is going to probe the hardware, just asking, hey, what's inside the machines? And we're just going to discover the hardware in a step-by-step manner. And the first question that we ask to the motherboard, give me your system ID. And based on the system ID, we can configure the BMC image. Then we want to deliver also the RAM through the network. And that is something which is important, because when you provision and when you want to run a zero-touch provisioning, you want to update everything, because you do not trust the machine when it's coming into the data centers. You can trust the system only when it is going to run a firmware version that you know and that you own. So, and the first step that we do is we push this firmware version to the machine. So we have a very basic OpenBMC image. It discovers the hardware. Based on the hardware discovery, it is requesting from the backend systems into the data center the specific RAM which is needed to start the host. And it is retrieving it from the network, And based on that, we can flash it locally and we can deliver that to the host and we can start up the host. So one of the benefits is you don't need to know what kind of hardware you are going to deploy, and that's super generic. And the image does include everything. So that's a slightly bigger image, but we can manage the storage, and I'll be explaining what we have done just to do that. Our primary goal with that approach is to try to design systems where we are delivering hardware without any software into the hardware. So we also have many customers which are complaining about the security through the supply chain. So when the server is getting out of HPE manufacturing, it goes through FedEx or it goes through any kind of forwarders. And you can have bad people in the middle. Not saying this is happening every day, but this could happen. And we have more and more customers which are telling us, is there a way just to ship a machine without any software? And getting the software just when the machine is hitting the data center. And this is what we are trying to achieve. And what we are doing with that approach is to say, if we have a common OpenBMC image, and if we have some hardware which is just booting from the network, so we just configure the BMC, and the BMC is just requesting something from the network. So you power up the hardware, and you say, okay, I'm here, I'm alive, just send me what I need to feed me. And this is what we are doing with that approach, including the system ROM. And we're working on the PCI Express devices. How can we update them before even turning on the host? Just to be sure that all the software which is delivered to the hardware platform is something that we know and that we can trust.
What about any other compatible firmwares? Like, so BMC is one of them, but like if any other component like BIOS or...
We do it for the BIOS. So for the BIOS, we do not trust the BIOS which is on the motherboard with that approach. We just retrieve the BIOS from a trustable website, which is hosted into the data center. We can do it for some PCI Express endpoints, because all PCI Express cards currently have a local firmware most of the time, the GPUs, the network adapters, even the storage controllers. So as soon as they are supporting MCTP and SPDM, which are local protocols just to provide firmware updates, we can do that remotely. And before turning on the machines, we can update everything. So this is what we are doing right now.
Okay.
Yeah, this is getting kind of common that you don't know how long your hardware is going to be in the shipping and the manufacturing state. That you want your most up-to-date software. And thing even done to when engineering wasn't finished, that we had some package that we sent out equipment that didn't really do anything. All it did was load our software, so that we got that 2 or 3 months to have a package to download.
Yeah, I think my thinking currently is not to say we want the most up-to-date software. It's more to say I want the software that I know. And that I can trust.
There's also this protection. Right?
Yes.
There's also this
so it could be up to date, or it could be aging. I mainly do not care. I'm more caring about, can I trust the software which has been loaded on this machine? If the answer is yes, then I'm good. So I know the state of the system. So that's the key thing.
Now, if they are worried about their system, about something bad's gone into their system, can they go back to the original? Is there a wrong with the original start?
You'll be seeing what we have done later. Yeah. So what we do roughly is, in that configuration, all of our machines are always booting from the network. So roughly the default, at least within that setup, is really to say the device is a device. It's no longer a server. It's not autonomous. It has to be connected to a data center infrastructure, and that infrastructure is trusted. I'm not trusting the client, and the client is always booting from the network, and it's getting everything from the network. And if you want to run a rollback, you just need to change the backend configuration and say boot from that version or boot from the previous one. This is super easy to do. This is just switching one file on the backend. And then you reset the machine, and it's restarting from the rollback.
Okay.
So there's
Yes,
that roughly there's no software inside the machine. Everything is coming from the network, including the ROM, the BIOS, and the BMC image.
Mhm.
So just to make it work as being, I don't know how familiar you are with Linux, so you're probably not that much familiar, but when you build an embedded Linux image, you need to describe the hardware on which that Linux kernel is going to run. So you need to describe where the peripherals are and what kind of peripheral they are, like that's a serial console, that's a serial TTY, there is a network adapter at this specific PCI Express address. You describe everything.
Yeah, there's the DCT file.
That's a DTS.
Device
file.
Yeah,
DTS.
device 3 file.
Okay.
And what we have done, we're just using what does exist currently, but we are just using it at the BMC level. So we break down the device tree in two subsystems. We have a very generic device tree, which is just booting the BMC ASICs. So, and that device tree is just focused on the ASICs itself. It doesn't care about anything related to the host. So we just want to start the ASICs. And when we have started the ASICs, we have what we call the device tree overlay. And that overlay is going to have the feature which are specific to the host.
Mm-hmm.
So roughly, we describe the I2C bus, but we do not describe into the generic device tree description the devices which are sitting on the I2C bus, because these devices are dependent on the host. They are not dependent from the ASICs. So the ASICs is just telling us, I got 7 I2C buses. There might be a ton of various devices connected to that.
Right.
But when I'm starting the BMC, I don't know these devices, because I need to know on which host I am running just to know the address of the devices. So the first step is really to have that basic device tree. And the second step is per host having a device tree overlay which is describing where are the devices. So we broke down the device tree in these two steps. And we first start the Linux kernel with the very basic device tree. And during the boot process, and so within the init ramfs of the Linux kernel, we are going to run the system ID from the EEPROM of the motherboard. And based on the system ID, we can retrieve the right device tree overlay and apply that overlay to the Linux kernel. So this is what we do. And like that, we can be generic enough just to start the same image on all Proliant family, because the device tree configuration is different between Intel and AMD or Ampere, but we put the dependency into the overlay. So within the image, we got 3 overlay, one for Intel, one for AMD, and one for Ampere, but we just load the right one. So with the current standard OpenBMC build process, you have to have one device tree which is specific to the system target you are building for. So we change all of that, and we say, no, that's not the good approach, at least for us and our end users. And we got these 2 device trees now.
So the system ID is the one that tells you this is like Intel 4th gen processor
Yes.
system.
Yeah.
And then you find the right images.
Yeah,
Or
so
load them.
roughly what we have is, on our servers, we have a CPLD, which is just a small FPGA, and the system ID is written down into the CPLD. So, and this is the script that we use to replace the init script into the init ramfs. So before calling init, we are using that script. So we retrieve the system ID. This is just right here. And this is just by reading one of the registers from the CPLD. And based on that, we update some environment variable for systemd, because the boot flow is going to be affected by the system ID. So the fan control table, for example, some of our systems have 5 fans and others might have 7 fans. So the user space needs to know on which system it is running. And based on that, it will be configuring only 5 fans or 7 fans.
Right.
So we expose the system ID into the user space, the upcoming user space environment, and then we apply the overlay there. So we mount the config.fs, that's the interface to apply the overlay within the Linux kernel. and then we retrieve the ProLiant DTB, which is the device tree overlay specific to the server on which we are running, and we apply it by issuing this command. So this is just pushing the device tree overlay to the Linux kernel. And when it's applied, we can execute, we can pursue the normal boot flow. So we execute the systemd init. This is just a hook inside the boot flow. So.
Yeah.
So then the second issue is we had a customers which is exposed to some challenges during Black Friday. He said, I got some peak consumptions which are coming up. And it's crazy when you think about it. If your sales is dependent of Black Friday, that might be the case at Amazon. But that's not Amazon. So that's another customers, but they are strongly affected by Black Friday. So they have to provision a massive amount of systems at a very fast pace. And by using the traditional firmware update and traditional processing of image updates, it was way too long for them. And even just to update the BMC image, it could take 5 minutes. And they say that's way too long because we have tens of thousands of systems just to update, and we are losing way too many of them during that process. So we just want to get rid of that. So what can we do? And how can we update this machine as fast as we can? So we got that crazy idea because we are booting from the network. We said, okay, so instead of storing the BMC image inside the machines, why not using block storage, network block storage, to retrieve the BMC image? So this is just like having an hard drive which is not inside the machine, but it's connected to the machine by using the network. So this is using iSCSI protocol, but it could be using other protocols. So it could be, I don't know, ATA over Ethernet or whatever you might be knowing as a low-level protocol. And we took that crazy decision which says, hey, can we boot by using iSCSI, the BMC? And if we could do that, how fast will it be? And what we discovered is we can boot 2 to 3 times faster the BMC by using iSCSI rather than using local storage. The main reason behind that is when you use local storage, the file system on the spinal is compressed because the spinal is too small just to make fit a BMC image. The 16 meg or the 32 meg, that's too small. And everybody is using compressed file systems. But this has some implication when you start the BMC, because it has to uncompress the file system on the fly. And when you are using iSCSI, you don't need to compress the file system, because usually you are using a backend storage which has plenty of storage. So you do not have that constraints of the local storage, which is way too small. And the network is fast. So most of our BMC networking card can run at 2.5 gigabits per second, which is way much faster than the local SPI part. Mm-hmm. So you can benefit from removing the compression and using faster storage bandwidth.
Now, are you using this to do the actual boot, or are you using this to
boot the BMC, to boot the firmware?
Or so you're booting BMC using a remote iSCSI drive?
Yes.
Or are you, okay, at first I thought you were taking an iSCSI drive to replace your SPI code.
That's about the same thing, because the SPI code was containing the operating system for the BMC. Mm-hmm. So what we have done is we tweak U-boot, which is the bootloader for OpenBMC, and we configure it into a way where it is issuing a DHCP request. It's getting an IP address. When it's getting the IP address, it is retrieving for a TFTP boot image. It's getting a fit image which contains the Linux kernel and init-ramfs. And within the init-ramfs, we are mounting the root file systems from the iSCSI protocol instead of using the local spinal. So we fork that approach, but it is way much faster, and you can the other key advantages into this case is that you can set up the iSCSI storage at a very fast pace and before Black Friday. And when you have to switch the systems, so they just boot on the new storage. You don't need to update any content on the servers. They're just booting from the network. Everything has been prepared up front. So you don't need to touch your infrastructure. So if the infrastructure was used for something else, you can switch in 10 seconds.
So you don't really need.
You don't need
ROM.
to touch you don't need a ROM. You don't need to touch the hardware. So you just need to restart it.
But you can do this because you're not portable, and the machine is at a static place and pulled in all.
Yes, that's because this is into a data center. But you can reallocate the platforms from one task to another one at a very fast pace.
Yeah. Okay.
And that's the use case scenario. Mm-hmm. Because when you get a peak of production, so that systems was doing something else, you reallocate them to something very specific during a very short period of time, and then you have to reallocate them back to their previous task.
So you're building full servers, and then you're saying, okay, I'm going to move 100 from doing one task to a different one.
Yeah, I want to reconfigure everything at the fastest pace as possible.
So they're all configurable.
Yes. And we have done that by using another open source software. So everything is based on open source technology. So we published everything. So if you want to play with that, just get in touch with me. I'll be sharing the source code with you. It's super easy. But this has some impact on the DHCP infrastructures. So we pick up core DHCP. That's a Meta project. It's an open source project, which is an implementation of a DHCP servers written in Go. And we tweak it just to auto-configure the iSCSI boot. So roughly each time there is a new server which is coming up on the network with a MAC address, it is issuing a DHCP request. And the server is matching the MAC address with the database. And if that MAC address has been pre-configured, it is providing the iSCSI IP to the client. And the client is able to mount the iSCSI targets. And that's the whole process that we have implemented by using core DHCP. So it was not implemented into other DHCP servers. It was easier for us just to use core DHCP because it was written in Go, and that's easy to tweak. But that's also implemented, and you can remove and add servers on the fly through a very small web UI. So this is the modification that we have added into the init ramfs just to boot from iSCSI. It's super easy in the end. So the workflow is we issue a DHCP request from the network interface. We got an IP address. So then we set up the initiator names for the client. So if you are familiar with iSCSI protocol, there is initiator and target. The target is the server side, the initiator is the client side. It needs to have a unique ID, and that unique ID is usually a random thing which is generated during the boot flow. So we are just creating that unique ID for the client. So then we start the iSCSI services on the client. We create the log directory because into the init ramfs there's no default log directory. And then we issue a discover command. So requesting to the servers, hey, what kind of target do you have for me? And the server is providing you the target. There is a single target because there has been a unique MAC address authentication which has been done. And we can mount that iSCSI devices. This is what is happening with that command. And we can mount that a new device, which is usually SDA, as the root file system. So, and then we can execute a ch root into that root file system and run init from that ch root. And this is how we are booting from the network. And there's no longer any local storage into the server used for the BMC. So the last thing is how do we achieve seamless update? So that was the easiest part. So keep in mind, we boot from the network the BMC. We do not have any firmware anymore into the server. And as we are booting from iSCSI, we got plenty of storage. So instead of booting from 32 meg, we can boot from 200 meg or 1 terabyte or 1 gigabyte or whatever. We don't care. We can define the storage size. And we took the decision to boot from 200 meg. And by booting from 200 meg, we said, okay, we can use DNF, which is roughly an RPM package manager. And this is like Hume or RPMs or whatever. And by using the DNF, we can break down the whole BMC image in hundreds of packages. And we can update only the libSSR library, or we can update the XZ compressed binary. You have probably heard about that security threat within the XZ compressed algorithm during the past few weeks or days. So we really can update what's needed instead of updating the whole image. And this is way much more valuable and way much more efficient. And right now, we also can update the BMC without experiencing downtime on the BMC side. So a lot of customers were telling us, each time we have to update the BMC, we have to reset the BMC. And in some cases, when we reset the BMC, this has bad behavior on the server side, and we are losing production time. So by having an approach where we have package managers, we can update the SSL library without resetting the BMC. Because this is not the kernel. This is just the SSL library. So this is just an example. And this is super efficient.
It's like microservices.
This is like microservices, yeah. And we have applied that. So this is the 3 key things that we are leveraging currently with OpenBMC. And this is what we are trying to explain to people. When switching from proprietary firmware image to open source technology, just open your mind to how you can leverage open source advantages. So many people are just trying to re-implement the same thing than into the proprietary world with open source technology. It's okay, but what is the value for the end users? If in the end, this is the exact management process, the exact same pain, so the only one value might be the cost or the capability to rebuild an image. Yes.
Could it be that people who work in proprietary software just have trust issues?
It could be that.
I'm kidding. It's just a joke.
No, but
Well,
the thing.
There's testing problems.
Now there is a lot of value which can be perceived by the end users, but most of the time, the biggest value that you are bringing to an end user when switching to open source or something else is really not the capability to do the same thing than the previous things that you were using. It's really just to bring in some new way of addressing an issue. And that is why we are exploring booting BMC image from iSCSI. That is why we are exploring to remove all software from the hardware, just decoupling everything, saying the software should be on the software side and the hardware must be stupid and just coming up without any software. And that will be way much more easier from a security standpoint, from a provisioning standpoint, from a maintenance capability too. So that's the thing we are really believing into. I got a demo. I need to switch my screen, and I hope that the demo works. I'm not sure that the demo will work, but who knows? Oh, there's plenty of various buses. So on the BMC, there is USB, there is I2C, there is PCI Express, there is.
So it's just agnostic of any particular interface?
Yeah, it has to be agnostic. And usually the auto discovery is through I2C or I3C. I'm just connecting to my lab right now. It's probably, no, it's not too small. It's small, but it could be.
We can see it.
Yeah.
It's fine.
Okay. I don't know if the machine is up or not, so I'm just going to kill it. It's down. Okay.
So this DHCP package is Go language?
Yes.
Okay.
Okay, I got a system which is in Milpitas Labs. So that window is just to turn on the machines. So if everything goes well, you'll be seeing the BMC serial console into that window. So what I started here is the core DHCP stuff. So this is just going to provide the TCP/IP connectivity to the BMC there. And here you get the TFTP servers, which is running. So this is providing the initial Linux kernel image before we can mount the iSCSI target. So let me try to see if I can start the machine. Okay, the machine is starting, so I just turn on the power supply. And GXP ASIC is the ASICs from HPE. So you get ASPEED or Nuverton, which are competitors for the BMC ASICs. So HPE is still designing his own ASICs at the BMC level. That's based on an ARM CPU. Right now, this is a 32-bit CPU running at 800 megahertz. So it's currently checking the system security. So we got a silicon root of trust. And it is validating the boot block. And when the validation occurs, it will start U-boot. So U-boot is starting. And I'm going to interrupt the U-boot boot. Okay, so this is U-boot. I'm setting a load address for the THTP content. And then I'm going to issue a DHCP request. So the DHCP occurs. I got an IP address, which is coming from that servers. It's loading a default boot image, and that default boot image is about 7 meg. So this is containing the Linux kernel and the init ramfs. So then I'm going to boot from the memory. So this is just going to check the content, and it has detected a fit image at the address I set up before the boot. So it discovers a device tree, a Linux kernel image. So that is the initial device tree, and the init ramfs right now. The device tree is pretty small, it's 13 kilobytes. And this is booting the Linux kernel. So during the boot, so this is issuing the DHCP discover right now. It is going to request a new IP, and then it is going to issue the, let me interrupt the boot there, if I can. Yes. So let me get back there. That's the tricky, it's not the tricky part, but. So this is where all the magic happens. So here we are within the init ramfs. So within the init ramfs, we are turning on the networking. We issue a new DHCP request. We got a TCP IP address. We got a routing, so default route and DNS resolution. And this is where we are creating the iSCSI initiator random number. And then we issue the iSCSI target discovery, and we get an answers telling us, hey, that there is something which is available on the portal, and that's a 210 megabyte storage block device. And that storage block device is mounted to, is created within the init ramfs, and is going to be used as the root file system. So this is what is happening there. So we got the device attached to the BMC interface, and then we mount it as the root file system. That's ext4. It's not squashfs, it's not compressed. And then we apply the overlay. This is what's going on there. So we have mounted the iSCSI interface, and we know the systems we are working on right now. And we apply the overlay. So you can see that we got description for power supply, system power management, some drives, and some LED, and we discovered some I2C muxes and all this kind of thing.
Where did it get the system ID? Or maybe you showed it.
It's within the init ramfs script. Yeah.
Okay.
So I get the system ID within the init ramfs. We mount the file systems, and then we can apply the overlay, because the overlay is currently stored into the rootfs. So the first step is to mount the rootfs from the iSCSI and retrieve the overlay from the rootfs. Otherwise, we cannot get access to the overlay. The init ramfs is too small just to contain that data. So then we start the Linux kernel. So we apply the overlay, and OpenBMC is ramping up and starting. So usually it needs a few minutes just to recover the console. Well, no, that's because I interrupted the boot, so that's the key thing. Yeah, you have soon. Hopefully we'll recover it. Okay, here we go. I can connect to the machine. And when I'm running GF, you can see that the SDA is there. I never know how we can do that, but the SDA size is 200 meg. And this is the iSCSI device point. So we just booted a BMC without any local storage, everything from the network, and we apply the overlay, and we can get access to the OpenBMC interface.
Nice.
And really, the idea there is really to decouple the firmware from the hardware, and say the firmware shouldn't be into the hardware. And that's the software. I'm not trusting the software, or if I want to trust the software, it has to be into a place that I trust. And the hardware should have only as a capability just a way to retrieve the software from somewhere. So that's the key thing. So the next step to enhance that is where do we store the software? So I'm currently working at storing the software into the top of rack switches. So we made some crazy demo, and this is what I'm going to introduce at the next OCP Summit in Lisbon next week, or in 2 weeks from now. Is we modified the firmware from a network switch. So we created a special VLAN into that network switch, on which we have the iSCSI target servers which is running. So which means that when we get a BMC which starts, it is going to issue a DHCP request. And that there is a specific DHCP servers running into the network switch, which is going to answer for the public BMC interface, and with the VLAN IP configuration. And it is going to associate the target and the initiator through a specific VLAN for each servers which are connected to the network switch. So this is avoiding to have specific servers within the data centers to manage the firmware images. So everything could be sitting into the top of rack switches. The other advantages of using iSCSI, I got a lot of questions about why using iSCSI, is that we can build multipassing solutions. So instead of having one local storage area, we can have two top of the rack switches and two network interfaces per servers, and each of them connected to different switches, and configured into a way that there might be automatic failovers just in case one of the network switch fails or one of the network connections fails. So we can have very high reliable connectivity through that way. And this is what we are working on right now. And how can we update automatically these switches just to distribute automatic updates and firmware updates within the data center at scale? So, and that's totally different from what we are used to do during the past 20 years with proprietary firmware. So everything can be automatized and can be done at a very fast pace. So that's really the goal of that project. I'm currently working with 4 different POC sites on this technology, and what's amazing is that I introduced you 3 different IDs today, and these 3 different IDs has been coming up through 3 different sites. So they were sharing the same point of view in the end, independently, thinking, hey, that could be good if we could manage the firmware that way. Yeah. And when you think about it, this is getting closer and closer to an operating system. Instead of being a firmware, that's an operating system.
All the firmware becomes software.
In the end, the firmware, with UEFI and the BMC, the firmware is becoming more and more complex. And as it is becoming more and more complex, it needs a concept coming from the operating system world. And that is really the case, so we should be managing these things as being a full operating system. And I think when you think about it, or when you look at what we have been able to achieve in a very short period of time, so it took us probably less than 3 months is just to build all of this concept. That the main reason behind that is because Linux is mature, you can get access to all the software stack that you need, and we are just managing how we are integrating all of this. So this is super efficient. And we can enhance the security at a very high level with that approach too. This is what we believe.
So where these images are stored, the block storage or the rack switch, where you're saying this.
Within top of rack switches, you get more and more switches which can have a local NVMe drive inside the switch.
I see.
So you just put a local NVMe drive inside the switch.
And then you have remote access to just change the
you can put
update
150 gigabytes drives there. They cost nothing.
Yeah.
And you can supply BMC image to the whole rack.
How do you confirm that the software? How do you confirm that the firmware was successfully updated on the hardware?
As this is, there is a tricky things that you can apply, which is a little bit amazing. But on the switch, you can observe the BMC image. So you can check the BMC image because this is a remote block storage. So you can mount it locally on the switch in read-only mode. So which means that you can check that the content of the file system is behaving the way you are expecting it to behave, or is containing the software that you are expecting it to contain.
Okay.
The key thing is you get a block storage which is mounted through a network protocol, and the server who is providing that block storage can monitor the block storage locally. So that's the way you can make it happen.
Well, from your description, I could see how you can verify that the process was started. You can verify that there was interaction with the hardware, but how do you confirm on the hardware itself that you had the update that you wanted, or that it wasn't corrupted?
I think it has to boot off the network, so if it was corrupted, it wouldn't boot.
Okay.
That's the first thing. The second thing is you can sign all the software.
Okay.
So that's the key things during the boot process at the beginning. So there was secure root after start. It's checking the signature of the software, and it is validating U-boot. But we can pursue that UEFI that boot flow. So roughly that signature process up to the operating system level, and all the RPMs can be signed too. So that's the other things. So the package manager that we use and the RPMs that we generate are signed, and you can validate the signatures. So like that, you're sure that you're installing and deploying the RPMs you are expecting.
Okay. Thank you. And thank you.
So roughly, the idea behind it is you manage the firmware like you manage Linux on the host side. So if Linux can do it, you can do it at the firmware level. If Linux cannot do it, then you need to enhance Linux. So that's the key thing.
Right.
Linux, okay, if you're using APT or some sort of RPM package, that would mean you booted the kernel, and then you add the packages you want. Now, as part of the BMC, does it have a local RAM drive that it's keeping that sort of that's read-write data that's stored in Linux? Where is that? Is there hard storage?
Yeah,
as part of BMC or not?
You get the iSCSI drives. So the iSCSI drives is there, so you can store whatever you want on that.
Okay, but
and we create the database for the package manager into it.
Okay, but that means every machine has to have its own unique file system for NISCSI.
Yes. Yeah.
You're not. Okay, I was assuming that you were.
It's not read-only, so every machine has its own local file system for the iSCSI boot.
Okay, so but once it gets to the machine, it's strictly
Dedicated to the machine.
well. Oh, it's an ice. Okay, it's iSCSI for the hardware package, but most of it ends up getting cached in memory, so it doesn't
Yeah.
go out there very often. Okay.
But even if you get access pretty often to the device, so the device is running at 2.5 gigabits per second, so it's about 200 megabytes per second. A little bit more than 200 megabytes per second in read-write operations if you access to the storage area. So that's why you need NVMe into the switch. So that's still super fast when you think about it. For the BMC.
Oh yeah, for the BMC.
Yeah, I'm not speaking for servers workload or AI workload, but for a BMC, 200 megabytes per second, it's huge. It's really huge compared to the local storage that it can get access to, especially a spinal. A spinal is super slow.
Okay. But what's the typical memory that you're using in the BMC processor?
In terms of storage or RAM?
Yeah, and RAM. Yeah.
The RAM currently, I think that one, it's probably 512. I don't know if there's info. No, that's even smaller.
You might
That's
be able to do
300
free
meg,
dash M.
380. Sorry?
Oh, free space dash M, I think would do it.
Yeah, 380. I think that's 384 in that case. 384 megabytes. It's pretty small.
Relatively.
Yeah.
This stuff's
It's-
all relative, yeah.
That's one chip. Roughly what you might be expecting, that's probably a 512 megabyte chip.
Okay.
I don't know why I'm not using the upper level memory, but it's probably used by the video controller. Because there is an embedded video controller, there's a VGA card within every of our BMC. So this is what I'm working on currently. So just
Nice.
exploring what we can do and how we can change the way we think and we behave when thinking about firmware management.
Even those kinds of specs, it makes sense to run a general purpose OS. So,
Yeah, it could make sense.
Good, thank you.
Yeah, thanks for
I
the.
spoke too much.
No, it was good, like with all the introduction to BMC, and thanks for the sneak peek before the OCP. So
Yeah,
we are getting that
that's my demo
advantage.
for next week. So it's
Yeah, yeah. Thanks for sharing.
So, where are you doing